Picture this. It's August 2023. A massive typhoon, Haikui, is spinning menacingly in the western Pacific, heading straight toward Taiwan. Millions of people are bracing themselves, and they all need the exact same information. Where exactly is this storm going, and just how strong is it going to get? Now, for decades, there was only one way to answer that. But in 2023, something entirely new abruptly entered the weather room. 5 artificial intelligence models were asked to predict the storm's path. So in this explainer, we're going to look at exactly how AI learned to read the sky. To truly appreciate how wild this is, we have to look at the massive shift that just happened. For literally 70 years, weather forecasting has been ruled by traditional forecasting, what we call numerical weather prediction. It was the undisputed king. But then, almost overnight, AI showed up and totally flipped the script on how we predict the atmosphere. So, how did we get here? Okay, let's break this down. The old way, numerical weather prediction, relies entirely on the laws of physics. You turn atmospheric rules into massive, complex equations, feed them into a warehouse-sized supercomputer, and hours later you finally get a 10-day forecast. But around 2022, a wave of tech labs asked a different question. What if we just showed an AI millions of past weather snapshots and let it figure out the patterns itself? This is machine learning weather prediction. These models were trained on a dataset called ER5, which is this massive archive of global weather data from 1940 all the way to the present. The result? Instead of a supercomputer churning away for hours, AI can predict 10 days of global weather in mere seconds, literally running on a single GPU. It's a total game changer.
Act 2. 5 ways to read skies. Now, what's truly mind-blowing is that 5 major AI models were developed from that exact same Era 5 historical dataset, but they all learned in fundamentally different ways. It's kind of like 5 brilliant students reading the exact same textbook, but each taking totally different notes. Let's meet them. First up is FourCastNet V2, or FCN2. I like to call this one the patch cutter. It borrows a concept directly from computer vision called a vision transformer. Basically, it treats a layer of the atmosphere, like wind speed, as a giant photograph. It slices this global image into tiny square tiles, or patches, and uses frequency domain math to figure out how a weather pattern in one tile influences a tile on the complete opposite side of the world.
Then you've got Huawei's Pangu-Weather, which we can call the 3D thinker. Instead of looking at flat image layers like FCN2, Pangu processes the entire 3D atmosphere as one single massive volume using a Swin transformer. It analyzes height, latitude, and longitude all at the exact same time. It's almost like it's taking a giant MRI scan of the Earth's atmosphere to see how everything connects vertically and horizontally.
Next up is Google DeepMind's GraphCast. This one is the architectural outlier. We'll call it the network thinker. It completely ditches the idea of flat images or grids altogether. Instead, it treats the Earth as a massive network of connected points wrapped around an icosahedron mesh, kind of like a highly subdivided mathematical soccer ball. It doesn't care about pixels, it just asks, hey, which node is influencing the node right next to it?
And then there's FuXi from Fudan University, the relay runner. Here's the thing, when you ask a model to predict 15 days of weather step by step, tiny errors compound and snowball really quickly. FuXi avoids this accumulated error by splitting the job up. It uses a cascade of 3 entirely separate, highly specialized models, one for the short range, one for medium range, and one for long range. They literally hand the forecast off to each other, just like runners in a relay race.
Finally, we have Shanghai AI Lab's FengWu, the conversationalist. Most models just mash all the weather variables together into one giant input, but FengWu treats temperature, wind, and pressure as totally separate modalities. It explicitly learns the crosstalk between these variables, almost like different human specialists consulting each other in a room. Plus, it uses a replay buffer to practice recovering from its own forecasting mistakes during training, which is just incredibly smart.
Act 3. The race and the plot twist. So, from June to November of 2023, Taiwan's Central Weather Administration decided to run a thrilling apples-to-apples head-to-head race between all 5 models. They used the exact same starting data just to see who would actually win in the real world. When the dust settled on the overall accuracy, FengWu took first place, performing the best across most variables. FuXi was second, staying strong at all ranges. GraphCast took third, followed by FCN2 and finally Pangu-Weather. But get this, the traditional physics-based model, IFS, didn't come in last. It held its ground right in the middle of the pack. The old king wasn't dead yet.
But honestly, the real story of this race is what happened next.
During this evaluation, a shocking twist emerged regarding the 11 typhoons that struck in 2023. FengWu, our overall winner, was the absolute best at predicting exactly where those typhoons would go. It nailed the storm tracks flawlessly. But when it came to predicting how strong those storms would actually get, FengWu was the absolute worst. Think about that for a second. The best model overall totally failed at the single most critical task, feeling the storm's true punch.
Act 4. The intensity problem.
Now, this wasn't just some random fluke. Pangu-Weather, which came in last for overall accuracy, actually led in intensity prediction for several storms. This reveals a massive fundamental blind spot in how these models learn. Why were all of these incredibly smart AI models systematically underestimating the raw power of typhoons? Well, think about the number 28 for a second. Remember that ERA5 training data? Its grid resolution is about 28 kilometers per cell. But a deadly typhoon eyewall, which is the absolute core of the storm's power, is usually only 20 to 50 kilometers wide. So the training data literally blurs out the eyewall. The AI models have never actually seen a Category 5 peak intensity. They've only seen a smeared, averaged-out version of it on a coarse 28-kilometer grid. They hit a resolution wall.
And it gets worse, because there's also a statistical trap here, called regression to mean. Because these AI models are trained to minimize their average error, they are mathematically penalized for making bold, extreme predictions. If the AI is even slightly unsure, it just plays it safe and guesses something closer to the historical average. A 2024 National Hurricane Center study confirmed this exact thing. AI models systematically show a weak bias, predicting storms to be much weaker than reality, sometimes even losing to simple baseline guesses.
So how are researchers fighting back? Well, they're definitely not just throwing in the towel. A newer model called FengWu GHR uses transfer learning to push the training resolution down to 9 kilometers, allowing it to finally see that tight storm core. Another approach, RMSE AR, actually fuses the data with real satellite imagery, which has no resolution ceiling at all. And upcoming models like Bhagwan Cyclone are using highly specific subgrid modules designed specifically to extract those local extremes that the wide grid usually obscures.
Act 5. The power of the ensemble. But while we wait for those higher resolutions, the researchers in Taiwan discovered an incredibly satisfying and honestly somewhat counterintuitive workaround for right now. They asked, what if we stop trying to pick a single winner among these flawed models and instead use their differences to our advantage? It comes down to a brilliant 4-step realization. Because these 5 models have completely distinct architectures, the patch cutter versus the network thinker, they make totally different mistakes. If you just take the average of all their forecasts, their unique errors literally cancel each other out. The true shared signal is all that remains. By doing this, the researchers created a super predictor that completely eliminated catastrophic track errors. No single model had all the answers, but together, they were absolutely incredible.
And this isn't just some whiteboard theory anymore. Because AI models run in seconds rather than hours, running an ensemble of 50 models is suddenly as cheap as brewing a cup of coffee. This has already changed the real world. Europe's weather agency, ECMWF, pushed their own AI model, AIFS, into operational status in February 2025. And by July 1st of that same year, they launched a massive 51-member AI ensemble globally. The basic economics of weather prediction have been forever changed.
But before we throw a parade and declare total victory for AI, let's circle back to our cold open, Typhoon Haikui. When it hit Taiwan, it dropped over 700 millimeters of rain. A local Taiwanese physics-based model, which was running at a superfine 15-kilometer resolution, predicted it perfectly. The global AI models? They predicted somewhere between 130 and 200 millimeters. They were off by 3 to 5 times. And why? Simply because they couldn't clearly see Taiwan's 4,000-meter mountains interacting with the storm.
Which brings us to the big takeaway for this explainer. The story of AI weather prediction is basically the story of every powerful new technology. It is absolutely astonishing at what it can do, like rendering a global 10-day forecast in seconds and totally revolutionizing ensemble forecasting. But it is still learning what it can't do. For those catastrophic, extreme local impacts, AI is currently playing catch-up. It forces us to ask one final question. As brilliant and as fast as artificial intelligence is, does raw resolution still win in the end?